Hi, my name is Łukasz, and at first I would like to thank you for watching the video presentation of our work, which is enhancing chemical explainability through counterfactual masking, accepted to AAAI conference. In short, in this work we introduce a new masking method called counterfactual masking, specifically designed for molecular graphs. Why do we even need a new approach? Because standard masking methods are based on assumptions that are essentially wrong when applied to the chemical domain. First, I will try to convince you to that statement, and then I will present our method and show some results. As promised, I would like to start from saying, why do current masking methods fail for molecules? Let's say we have this molecule on the left, and we would like to see the contribution of the red fragment to the final prediction. The first and the easiest approach is to completely delete this fragment. However, in the case of small molecules, this often leads to two separate fragments. We no longer have a single connected molecule. This is a classic example of out-of-distribution problem, because our model was trained only on complete molecules. Because of this issue, we completely reject this approach for molecular graphs. What else we can do? We can zero out the features of all nodes in this fragment to assess its contribution. However, this also creates two new issues. The first is topology bias. We mask atom types and other node properties, but we do not hide the structure of the fragment itself, which leads to information leakage. The second issue is that zero features still carry meaning. One commonly used feature of the nodes is the number of heavy neighbors. If we set it to 0, it doesn't mean no information. It means that a given node has 0 heavy neighbors. In this way, we provide false information to the model. This leads to the main challenge, which we want to solve. Naive masking strategies, like zeroing features or deleting structures, often produce chemically invalid or physically impossible molecules. This in turn creates out-of-distribution samples for our models, resulting in unreliable or even random explanations. In general, we wanted to have a method that hides both atoms and bonds between them, but at the same time doesn't produce chemically invalid samples, as happens in these two methods. To solve these problems, we developed counterfactual masking. How it is working? In the first step, we delete all the nodes that we want to hide, just like in the previous method, but we do not leave the molecule broken. Instead, we fill the deleted parts using context fragment aware generation methods, creating as many chemically valid combinations as possible. In the best case scenario, we would like to generate all possible combinations in chemical space, not only 3 like in this example, but very often this gives us more than 300 alternative fragments. We then run prediction on all of them and average the results. Thanks to this approach, we get like average molecular property of all molecules where only the selected fragment is changed while everything else stays fixed. And what can we do now? First, we can compare our original prediction to this on average possible alternative. And here we can see that our red ring strongly increases activity compared to average alternative. And what is also nice in this method, if we would like to, for example, decrease the activity of the molecule, we have multiple examples from we can to choose from. All molecules in the red frame. And finally, after the introduction of our method, I would like to present some of our results. To conduct first experiment, we created a dataset of real molecules, which we match into pairs. In each pair, the molecules share the same core structure, not highlighted in red, and have different non-shared fragments, highlighted in red here. For each pair, we mask the fragments that were not shared and measure the difference in the model's predictions. We assume that an ideal masking technique should completely obscure the mask fragment, resulting in identical predictions for both molecules in the pair. In other words, the prediction difference between the two molecules should be equal to 0. For no-mask molecules, we got the average prediction difference of 2.81. With fragments masked by feature zeroing, the differences were slightly lower on average. With our counterfactual masking with difflinker, we got the difference of 1.81, and with Crane framework, we got the lowest difference, around 1.7. This can be seen in the histograms of differences for each method compared to the baseline. For no masking, we do not see any pairs with prediction differences higher than 8. In the case of feature zeroing, we get a few pairs with differences above 8. Do we expect that from a masking method? Not at all. We want our molecules to become more similar to each other, not more different, as feature zeroing produced here. Here are the results for counterfactual masking with difflinker diffusion-based method. Almost no molecule pairs show differences above 8, except for those two examples, probably due to generation of some chemically invalid molecules. And here counterfactual masking with Crane method. None of the molecule pairs have differences above 8. Great. And the mode of the distribution is close to 0, which is exactly what we wanted to see here. Here you can see the distribution of embeddings of molecules with zero-out fragments. Most of them are out-of-distribution samples, which can lead to unreliable explanations. Here we have the distribution of the same molecules masked using counterfactual masking with difflinker. We obtain samples much closer to the training distribution. And finally, molecules from counterfactual masking using the Crane framework. All of the masked molecules are in distribution, and thanks to that, the explanation based on them are the most reliable. And the main takeaway. Standard masking methods lead to out-of-distribution samples and unreliable explanations, while counterfactual masking produces in-distribution samples and more faithful explanations, thanks to that. Of course, the name of our method is counterfactual masking, and we can ask whether it is possible to generate counterfactuals. And of course, it is. How? First, we use a gradient-based method, for example GradCam, to identify the most important fragment for the prediction. With this information, we then replace the selected fragment with other fragments using generative methods. Thanks to these local changes, we create chemically valid and plausible targeted modifications in molecules, which can be easily interpreted by people with a chemistry background. Other methods often change the prediction class, but the resulting molecules are very often neither chemically valid nor contain targeted modifications. Here is a brief summary of our results. We achieve competitive performance on counterfactual generation metrics, but we perform better in synthetic accessibility, which means that we generate more realistic molecules. If you find our work interesting or would like to know more details, you can see it at the poster session on Thursday at AAAI, find the extended version on Archive, or access all the source code on GitHub. This work was presented by me, Łukasz Janisiów, a PhD candidate at the Jagiellonian University in Poland. I am a part of Ellie's PhD program, and my research focuses on explainable and interpretable machine learning in drug discovery. On the left you can see our entire project team from last year, and on the right the authors of the work I presented today. That would be everything from me. Thank you for watching this recording and have a nice day.